For more than half a century, rocket engines have represented the absolute peak of human engineering. Every curve, every channel, every bolt has traditionally been shaped by teams of engineers working for years, sometimes decades, refining designs through endless simulations and testing. Progress in propulsion has always been slow, expensive, and limited by human time and imagination. But in the mid-2020s, something quietly changed. Not in Silicon Valley, not at NASA, and not inside a traditional aerospace giant, but in Dubai, where a small engineering company began asking a dangerous question. What if rocket engines no longer needed to be designed by humans at all?
About a decade ago, I asked myself why innovation in the physical world is so much slower than innovation in information technology.
The reality is that engineering work is very repetitive. Now, if you always do the same steps, why shouldn't you be able to teach an algorithm how to do it for you?
It's our aspiration to help make engineering work much faster so that we can build all these amazing things that we all want to see around us.
That company is Leap 71, founded by aerospace engineer Josephine Lissner and technologist Lynn Kaiser. Instead of hiring massive engineering teams, Leap 71 built something entirely different. A computational engineering system called Neuron. Neuron is not a CAD tool, and it is not a simulation assistant. It is a physics-encoded system that autonomously generates complete engineering designs from first principles. Engineers do not draw parts. They define goals, constraints, materials, and operating conditions. From there, Neuron does the rest, calculating geometry, internal flow paths, cooling channels, structural thickness, and manufacturability on its own. In 2024, Leap 71 proved that this idea was not theoretical. That year, Neuron produced a fully functional liquid rocket engine design without any human modeling. The engine was 3D printed in copper alloy and hot-fired successfully, producing real thrust under real conditions. The entire process, from concept to test, took less than 2 weeks. What would normally take months or years had been compressed into days. This was the first clear signal that engineering itself might be changing. But Leap 71 was only getting started. In late 2025, the company escalated its ambition dramatically. In a period of under 3 weeks, Neuron autonomously designed 2 entirely different methane-powered rocket engines, each capable of producing roughly 20 kilonewtons of thrust. One followed a traditional bell nozzle architecture, the kind used on most rockets flying today. The other was far more radical, an Aerospace engine, a design that engineers had theorized about for decades but rarely built and never successfully tested at this scale. Both engines were fully 3D printed using high-temperature copper alloy, a material chosen for its exceptional thermal conductivity and ability to survive extreme combustion environments. The Bell nozzle engine performed exactly as predicted, reaching target chamber pressure and achieving combustion efficiency above 93%. The Aerospace engine, despite facing startup challenges, reached its intended internal pressure of 50 bar in its very first firing. Even a single successful ignition was enough to validate the design logic, because Aerospace engines are among the most complex propulsion systems ever attempted. What made this achievement extraordinary was not just the performance, but the process. These engines were not iterated through traditional trial and error. They were generated by a system that encodes physics directly into computation. Neuron did not copy existing designs. It solved the equations of fluid dynamics, thermodynamics, and structural mechanics simultaneously, producing geometries that would be nearly impossible for humans to invent manually. Methane was chosen deliberately. Methalox propulsion, using methane and liquid oxygen, is one of the most demanding propellant combinations in modern rocketry. Methane changes density dramatically under pressure and temperature, making it notoriously difficult to model accurately. The fact that Neuron's predictions aligned so closely with real-world test data was a critical validation of the system's depth and accuracy. According to Josephine Lissner, this level of fidelity shows that computational engineering can move beyond assistance and into autonomy. As these smaller engines were being tested, Leap 71 was already looking far beyond them. In November 2025, the company announced a major manufacturing milestone in collaboration with Nikon SLM Solutions, one of the world's leaders in industrial metal additive manufacturing. Together, they successfully produced a massive injector head for an orbital-class rocket engine, generating 2,000 kilonewtons of thrust. This injector, measuring roughly 600 millimeters in diameter, was printed as a single piece from in 718 nickel-based superalloy, a material capable of surviving the extreme heat and pressure of full-flow staged combustion engines. This component was manufactured using Nikon's NXG 600E system, one of the most advanced metal 3D printers ever built. The injector was not a prototype mock-up or a simplified test article. It was a fully validated production-scale component generated entirely by Neuron's computational design process. No human engineer manually modeled its internal structure. What began as an experiment in computational design is now becoming a blueprint for the future of engineering itself. In the years ahead, rockets may be conceived, optimized, and built in timeframes once thought impossible, opening the door to faster innovation, lower costs, and entirely new missions. The era where engineering progress was limited by human speed is quietly ending, and in its place, a new age is emerging, one where machines do not just assist creation, but actively shape the path of humanity.